This next topic is Chapter 5, Drug Identification and Analysis. The challenge with drug identification is trying to figure out what kind of a test to use to identify a particular drug. So there's two phases to it. The first is a screening test. It's preliminary and it reduces the possibilities. And then you have a confirmation test that will come after that that specifically identifies a substance. Preliminary analysis is called screening tests. Again, just reducing the possibilities to a manageable number. Often this is done by subjecting the material to color tests that will produce characteristic colors for the more commonly encountered drugs. Microcrystalline tests can also be used to identify drug substances by studying exactly like it sounds. Under the microscope, micro, very small shapes of crystals formed when the drug's mixed with different reagents. Different drugs will form different crystal patterns. After preliminary analysis, then confirmation is attempted to be obtained. There will be a specific test for every specific drug, and that will exclude all other chemical substances. The two main techniques that are used are infrared spectrophotometry or gas chromatography mass spectrometry, which we're going to abbreviate GCMS. And then for infrared IR spectrophotometry, SPEC. So one of those two techniques is used to specifically identify a drug. You also have to determine whether you're going to try to get qualitative information, which doesn't involve any measurements, or quantitative. The former, like I said, is just the identity. You're not taking any measurements. The latter is percent composition. We're actually working in numbers of the components of a mixture. First, we need to get into what chromatography is, and then we'll talk about different kinds of chromatography. We're separating a mixture, basically. Separating and identifying the parts of a mixture. You can see what's happening here. There's gas phase and a liquid phase. Air is moving across, and it's separating the components, gases and liquids. Those two different parts move across at different rates. The basis of chromatography is that chemical substances can escape into the surrounding environment when dissolved in a liquid or absorbed on a solid surface. They either will have a preference for whatever is moving, whether it's a liquid or a gas, or they'll have a preference for the solid, which is the stationary phase. It's not moving anywhere. We'll do thin layer chromatography. That's one of the labs that we're going to be doing. It's the solid stationary phase. That's a silica gel that's on a backing of plastic. We don't have glass, it's plastic. And then a mobile liquid phase, which is this really stinky solvent mixture. And that will separate the components of a mixture. The liquid will rise up the TLC plate by what we call capillary action, the absorption of liquids. And that sample then will become distributed. It'll be separated depending on which parts like the stationary phase, the TLC plate, better, and which ones like the liquid phase better. Most of these compounds that we're going to be working with are colorless, and so we have to use the UV light to be able to visualize what's going on. The distance a spot travels up a thin layer plate is called the RF value. And the RF value is calculated, I'm going to draw it over here on the side, RF is calculated, but the distance the dye travels divided by the distance the solvent or the liquid travels. Oops, I ran out of room. Liquid. It doesn't have a unit. There's not a unit for RF. It's unitless. You don't have to know what a GC is made of. We're going to switch kind of gears to gas chromatography, or GC. You don't have to know all of the insides of what a gas chromatogram looks like, or chromatograph. But you do have to know that there's gas inside, and usually it's helium. The stationary phase that doesn't move through is a thin film of liquid. So a mixture will go through this gas column and it will separate into its components. So what you see here on the left-hand side, we have two different barbiturates that are being separated. And depending on the identity of the substance, it will stay in the chamber for a certain amount of time. It's called retention time. And then on the right-hand side, the right-hand gas chromatogram, we have lots of different drugs that are mixed together there. These series of peaks and valleys are called a chromatogram, and like I said before, the time that a particular chemical stays in the GC column is known as retention time. And retention time is unique to all different substances. Now on to spectrophotometry. So sometimes a substance will absorb visible light, sometimes it will absorb invisible radiations. Spectrophotometry uses both of those depending on what kind of machinery you use. It measures the amount of radiation a particular material absorbs, and we can compare this based on wavelength and frequency. Different wavelengths and different frequencies are tested. Most forensic laboratories use ultraviolet and infrared specs, spectrophotometers. The nice thing about UV is it's really simple. It makes it easy to determine a material's probable identity, but it doesn't give an actual foolproof result. The IR spectrum, on the other hand, is sometimes compared to a fingerprint of a substance. It is a unique identifier. And that's what I just said. Different materials have distinctively different infrared spectra. So each of those is a fingerprint. Here we see the IR spectrum of heroin. And the wavelength is, you see a peak at the wavelength just under 300 nanometers. And that's the wavelength of light. Specs are used, again, to measure and record the absorption spectrum of a substance. We can do this using a visible spec, a UV spec, or an infrared spec. We already talked about the differences between those. There's also a mass spectrometer. You don't have to know how it works. You do know that it's usually paired up with a gas chromatograph. So the high energy ions going through the mass spec, the material that's in there will be separated according to its mass. So the mixture is separated according to the different components' masses. It's unique because under carefully controlled conditions, no two substances will produce the same fragmentation pattern. So mass spec also can give you a unique identifier. A lot of times GCs and MSs are coupled together so that the GC separates the components and then the mass spec will identify uniquely the different components. So the separation is done by the GC, and then each of those components is busted apart with the high energy electrons in the mass spec. And again, that's like a fingerprint of the substance being examined. What you see here are two different mass specs of two different chemicals. So you see different peaks along the way. It's a peak here, a little peak here, a little peak here, a little bigger peak, 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 like that. So that's from the GC. And then within each peak, you see the different components that's been broken apart. That's what the MS does. Collection and preservation of drugs. Use your common sense. Use what you learned at the beginning of the semester. Evidence has to be properly packaged and labeled. Got to prevent the loss of contents and cross-contamination. So package everything separately. Sometimes the original container will be a great place to package things anyway. Packages have to be marked so that we can identify the officer and establish the chain of custody.